Hello, and welcome to Aggressive Physics. Today is day 44, and what we're going to look at is drawing free body diagrams with inclined planes. Now, inclined planes pose a new challenge to us because instead of having an x and y direction, what we're going to do is take our axis and effectively tilt it. So our x and y directions still exist in the real world, but the surface, instead of having an angle on the object resting on flat ground, the surface itself is going to be twisted or tilted. So the inclined plane poses a new problem for free body diagrams. In fact, it gives us our one opportunity to draw more than one object within the free body diagram. And it seems to be the only case where that's allowed. In fact, if we were to draw a free body diagram for a car resting on a hill, then what we would do is draw the hill, the incline, we would make it a right triangle, and then we would draw the car onto the hill. Now, we're always going to use rectangles to represent free body diagrams. It just makes it a lot easier. That way, if we have oddly shaped objects, it may seem like some of those odd parts of the shape have forces acting on them in the first place. So what we're just going to stick to is boxes. So I'm going to draw the car, but now the car is not going to have a rectangle that seems to be oriented to the ground. It's going to be oriented to the inclined plane. Now, gravity is always going to act straight down, but the motion of the vehicle is going to be down or up the incline. So gravity is not going to be perpendicular to the motion of the object. In fact, only some of gravity is going to contribute to moving the object down the hill. The rest is actually going to contribute to the normal force. So an inclined plane is a special case of free body diagrams where gravity actually needs to be resolved into components. Now, I like to call it brake legs of gravity. So what we're going to have to do is resolve the vector of Fg, or W equals mg, if that's what you want to use, into its components. And the way we do that is by using trig. And trigonometry is going to be the way we're able to determine the legs of gravity. But what's odd is that the gravitational pull is our hypotenuse, and then the legs are going to be the legs of the triangle, but it's not a right triangle that is common for us to view. Normally we draw right triangles so that the right angle is either in the bottom right or the bottom left of the triangle. We often draw the right triangle so the legs go along the x and y directions, and the hypotenuse is at an angle, as if we were drawing a linear relationship on a graph, let's say. But now all of a sudden we have gravity going down and the axis itself is twisted or tilted. So the way we need to deal with that is by looking at the triangle almost inverted and flipped. And what I'm going to do in a little while is show you the example of this on the whiteboard. I think it's very difficult to visualize. But gravity is going to be our hypotenuse. We're going to draw a line that is parallel to the incline itself, up into the left if it's a incline that's down to the right, and then we're going to connect that line to the surface by drawing a line to the vehicle itself, or in this case to where gravity is, to complete the triangle. That means we're going to end up with a parallel force parallel to the incline and a perpendicular force perpendicular to the incline. So instead of breaking the incline up, we leave the incline alone, and instead we force the other vectors to play with the incline itself. So we take our x-axis and we tilt it, we twist it a little bit, either uphill or downhill. Now, in order to calculate the two values, we would use sine and cosine. In order to find f parallel, we would use the weight of the object, so Fg, times the sine of theta. In order to find the perpendicular component, it would be Fg times the cosine of theta. So each of the components can be found by using trigonometry. What is the only difficult part of this is that you have to worry about the fact that the triangle isn't visually aesthetic. in terms of our normal view of a right triangle. It looks different than we're used to. It doesn't mean it's different, it just appears different than normal. Now, that being said, if we look at F parallel and F perpendicular, they have specific purposes in our free body diagram. F parallel is going to be the force that moves the object down the incline. In fact, if there were no other forces, and let's say the emergency brake left, failed on the car would travel down the hill due to only the F parallel. It wouldn't fall at a rate of 9.8 meters per second squared. It would be much less. In fact, the F perpendicular is going to be perpendicular to the surface, so it's going to contribute to the normal force. It may not be all of the normal force because there may be other angled forces involved, but it will contribute to the normal force in the fact that it will be part of Fn. So when we then find the equations, let's say we're looking for some unknown, we would use parallel and perpendicular as our directions instead of x and y. So what we have is gravity, which needs to be broken up to fit within the confines of our new equation. It's something different because normally we would fit into the confines of gravity, but in this case, this is our one chance to get gravity back. Gravity is always dragging us down, so now it's our turn to fight back. And in fact, we're going to blog to do it. We're going to break legs of gravity. Now, if we were going to solve a problem with inclines, we would do very similar steps to what we've done before. We draw our free body diagram. The major difference is that we would have the incline drawn as well. So we'd have a triangle and the object itself. Then what we would do is we would draw gravity. Gravity acts straight down. Just because there's an incline doesn't change the gravitational pull of the Earth. The Earth is going to pull objects straight down to the center no matter what. At that point, we don't use gravity as its full value. Gravity is now a hypotenuse, and we're going to break legs. It's like any other angle. What is strange about this is that the angle of the incline happens to be the same as the angle of the hypotenuse itself. And that's due to the fact that we have similar triangles. And the triangle of the incline and the triangle of the of gravity are similar triangles, so they share similar angles. They may not have the same values, but they share angles. Now, that being said, what we're then going to do is look at all the forces along the incline and say that that's the parallel direction. So we're going to sum the forces in the parallel direction and set it equal to ma. Then we're going to look at the perpendicular direction, sum all the forces equal to ma in the perpendicular direction. So once again, we'll have two equations. We could solve up to two unknowns, and we can solve fairly complex problems. And what we'll do is some sample problems with that. But for now, what I'd like to do is take the whiteboard out and look at showing you exactly how to draw the triangle for the incline, how to draw the perpendicular and the parallel forces of gravity, and just show you the general setup for a practice problem dealing with inclined planes and free body diagrams. So the only new thing now is that we get to draw the incline itself, and then we also get to break the legs of gravity. It's payback time. Thank you. So we're going to draw a free body diagram for an object that's resting on an incline. And an incline, remember, is just a fancy word for a ramp. So what we have is the object, and it has a certain mass. And we want to figure out the forces acting on it. Now, if it's just sitting on the incline itself, gravity is always acting, but gravity acts directly down. So that's going to be Fg. And if the mass, book, car, whatever it is pushing on the incline pushes back. And we call that the normal force because it's the force caused by the surface. Now, you'll notice here that gravity and the normal force are not aligned. The normal force is tilted. In fact, it's turned based on the angle of the incline. Now, this angle of the incline is going to be important because what we're going to do now is force gravity to conform to the incline itself. Normally we would, in other problems, if it was flat ground and we had an angle, we would break the angle up and force it to be in an X and a Y direction. But since the incline is basically a coordinate axis that's just tilted, what we can do is use the incline as an axis. And in fact, what we're going to do is effectively turn the incline into parallel to the incline and perpendicular to the incline. And as long as they are 90 degrees apart, well, we know perpendicular vectors are independent. And since forces are all vectors, we're going to be able to solve for two different problems, the parallel and perpendicular. So how do we break gravity up? I actually call it blogging. We're going to break the legs of gravity. Break legs of gravity. So we're going to blog. And the way it works is we want a part of gravity that is perpendicular to the incline and part of gravity that is parallel to the incline. And the odd part about this is that the triangle I just created is a similar triangle to the incline itself. And this angle in here happens to be the same as the angle of the incline because of congruent parts of congruent triangles. Now, this is not a right triangle that we're used to because the right angle is over here. So if I were to redraw it a little larger on this side, here was force of gravity. Here is the perpendicular, and here's the angle. So what we could actually do is twist this around and draw it in the manner we normally see right triangles. Here's the incline, here's the angle, the right angle, and the angle that we have. And this happens to be gravity. Gravity is the hypotenuse. And this part is usually what we'd call X and Y. But the one touching here as we twisted it is actually perpendicular to the incline. So I call it F perpendicular. And this is parallel to the incline. So I call it F parallel. Now, in order to do the math for this, what we're going to need to do is trig. So taking this, and when I twisted it to get the right angle there, that's F perpendicular, and that's F parallel. Well, we've done enough trig by now to realize the one touching the angle should be cosine, and the one opposite the angle should be sine. So in order to find the legs of gravity, you're going to do F perpendicular equals FG cosine theta, and F parallel is going to be FG sine theta. Now, parallel is going to move it down the incline. That's going to be the motion of whatever the mass is. F perpendicular, well, that's going to be equal and opposite in many cases solely to the normal force. If we look at the problem as I drew it, there are only two arrows in the perpendicular direction. And those two arrows are Fn and F perpendicular. One goes up, so I'm going to call the up perpendicular positive, and the down in the perpendicular axis negative. Fn minus F perpendicular equals 0. So many problems, once you find the F perpendicular, that will get you the normal force. Now, why is the normal force so important? Well, it's going to be a vital component to friction when we start calculating friction. And that's not too far away, so I mentioned it now so that you realize that it's important to know how to use it. So finding it is valuable today, and then in a couple of days, we're going to be able to use it to actually calculate friction, and that will allow us to solve more complex problems. So due to geometry and the fact that triangles that are similar share similar features, we're able to take the incline's angle, use it to break the legs of gravity, and then now gravity conforms to the incline, and we're left with a force down the incline, which is going to actually cause it to move. In many cases, that was our F applied before. And then our other force is going to be perpendicular to the incline, and that's going to contribute many times solely to the normal force. So just remember, trig, cosine, and sine will allow us to break legs of gravity. Now let's look at an inclined plane accelerating a ball down a ramp. Now, for the scope of this course, we're just going to use regular motion, translational motion, which is straight line motion. But when we have balls or cans or hoops or things like that, we also have rotational motion involved. And there will be other equations that you'll be able to use to better simulate that type of motion. In fact, a ball and a hoop will both act a little differently when moving down a ramp. But for our purposes in this course, we're just going to look at the straight line motion as if all the mass is centrally located in the ball, and the ball is just moving, almost sliding down the ramp. For small angles, for short distances, we typically get fairly good results, even with objects that do have rotational motion. But as you move forward in physics, you may find that you'll study rotational dynamics as well, and talk about things like moment of inertia and angular velocity and angular acceleration. And that will change some of the solutions that we get now. But if we just look at a generic problem where an object, and this could even be an object that's sliding. The problem is there's so much friction with sliding that we often use wheels to help simulate acceleration anyway. I'm just going to draw the free body diagram with a block. Even though it's circular, I still use the block. And we have a ball, and let's just say the ball has a mass of 1 kilogram. We'll just make it easy on ourselves. So this is 1 kilogram. Okay. The free body diagram would look like this. There would be a downward force of gravity. There would be the perpendicular force and the parallel force. So parallels here, perpendiculars here. And I want to look at 3 different angles. I'm going to look at 30, 45, and 60. Now hopefully we can come up with a consistent equation and then plug in the angles. I don't want to do this problem 3 different times. Now the perpendicular force is opposed by the normal force, so they'll be equal. And since I used 1 kilogram, we have 1 kilogram times 9.8 meters per second squared, and probably don't need the calculator for that, 9.8 newtons. Now generically, we're going to have F parallel become FG sine theta, and F perpendicular is going to be FG cosine theta. Well, the cosine is going to contribute to the normal force, and actually that'll help us later when we deal with friction. But for now, I'm just going to say Fn equals F perpendicular, which is going to equal Fg cosine theta. And we know that Fn then equals 9.8 newtons cosine of whatever the angle is. And that will be important in another couple of days when we start dealing with friction and the normal forces. But for now, we'd leave it in that form. We don't know the angle. I could put in cosine 30, 45, or 60. Now, if we look at the problem and there's no friction, the only force moving the ball down the incline becomes the F parallel. So F parallel is the only force that contributes in the parallel direction. So this over here was my sum of the forces in the perpendicular direction. And if I sum the forces in the parallel direction, I get F parallel equals MA, which is the simplest type of equation for forces, only one force in the direction of motion. Now we know that F parallel is Fg sine theta equals MA. All right, we know Fg is 9.8, so 9.8 newtons times sine theta equals 1 times A. And what we can do is find the acceleration, since the 1, if I divide the 1 here, we have A equals 9.8 sine of whatever the angle is. So at 30 degrees, 45 degrees, and 60 degrees, we're going to get 9.8 sine 30, 9.8 sine 45, 9.8 sine 60. Let's see what our three answers are. I would imagine that as you get bigger in terms of the angle, the acceleration gets larger. But let's see. 9.8 times the sine of 30 is 4.9 meters per second squared. 9.8 times the sine of 45 is 6.93 meters per second squared. And 9.8 times the sine of 60, I bet it's the biggest, 8.5 meters per second squared. Now we can easily do this in the laboratory setting, where we could take an incline and roll objects down the incline at different angles and see how close we come to the accepted values. Now, what I didn't mention before is that Fg, if you remember, is actually mass times gravity sine theta equals mass times acceleration. So we could actually simplify this even further, cross out the m's, and anytime you have an inclined plane with no friction, your acceleration is based on g sine theta. So all you have to do is take 9.8 and multiply it by the sine of the angle, and that's your theoretical acceleration. At 30, it's half. At 60, it's 8.5. Now, remember, if we have a flat inclined plane, the acceleration should be 0. And if we have a vertical inclined plane, it should be 9.8. So these answers are all going to be between 0 and 9.8.